Well, Happy New Year, everybody, and welcome back to another episode of our Flip Classroom. And hope you had a great break, and I hope you're ready to get back after it. Well, I have some bad news in the sense that I wish I could give you a real nice, easy topic here today to kind of ease you back into it, but no such luck. In fact, we've got our hands full as we begin, and we've kind of been foreshadowing there a little bit before break that we're going to get into this thing called a power series. And basically, a power series is now a series that is expressed in both terms of x and n. So the general form is going to be a sub n times x raised to the nth power. We're going to get in the habit of usually starting these at 0 more often than not nowadays. And again, all I want to stress here is that it's in terms of both n and x. X is going to stay in x for the most part. And so I want to just kind of get a few things out in the open here. We kind of want to establish a theme here. What are we going to be doing a lot of over the next few weeks? And our theme is going to be, we're going to be continuously finding a power series in order to represent a specific function. Okay, that's going to be our goal over and over again. Can we find a nice perfect match to represent a specific function? And we're going to use the traditional notation here, such as I'm going to use probably capital F's more times than not for a power series. Can we find a function that is a perfect match for the series a sub n times x to the nth power all the way to infinity? Now, what's interesting here to maybe make a note of is if I don't use an infinite series, let's say for some reason I went from 0 to 1,000 and I stopped there. I didn't go all the way to infinity for some unforeseen reason. I wouldn't be able to say equals. I'd then say that f of x is approximately equal to that. It's because we're going all the way to infinity that we create the perfect match, and we're allowed to now use that equal sign right there in the middle. Okay, now we want to establish, okay, we've got our theme. Now, why in the world would we want to do this? Well, the big reason is the power series that we create, okay, that are in this form. When we expand them out, and we start plugging in a 0 for n, and a 1 for n, and a 2 for n, and all the way out to infinity. When we start to expand them out, they create a polynomial. And the key here is polynomials are extremely friendly compared to other types of functions. And basically, a polynomial is, well, we know what a polynomial is, and then the opposite of a polynomial would be a transcendental. And a transcendental family includes everything like e to the x, natural log of x, and all those trig functions. And basically, anything that's not a polynomial then falls into the transcendental family. And that's why we like our power series, because it's significantly easier to differentiate, and I'm going to abbreviate here, and also to integrate a polynomial compared to a transcendental function. I'm not sure if I'm spelling that right, but we'll say that that's close enough for today. But yeah, it's significantly easier to differentiate and integrate a polynomial compared to a transcendental function, and that's the real reason that we pursue these power functions, and mathematically speaking, we have such a connection with them. I want to spend a little bit of time giving you an example. Now, before too long, you're going to find out, and you're going to be very good at building a certain power series for e to the x. It's one of the first easiest ones we're going to do here in the next couple of days. And you're going to find out that e to the x is equivalent to a power series that looks like this. Okay, x to the nth power divided by n factorial. It's kind of a fun looking one, isn't it? And you're thinking, well, I don't really see the advantage of that because I can differentiate and integrate e to the x quite easily. However, once you know this, you're then going to be able to build a power series for this function. I want you to think about e to the x squared plus 1 maybe, okay? And you're going to easily be able to build that power series. I promise you, you're going to be able to do that quite easily. And think about taking this guy's derivative, 3 or 4 times. The first derivative wouldn't be bad, would it? Not at all, okay? We'd end up with something like 2x e to the x squared plus 1. But now, all of a sudden, for that second derivative, I got to start to use the power rule. And then it's just going to get messier and messier and messier. And if for some reason, as an engineer, you had to take 10 derivatives of this function, I mean, your head would explode. And therefore, we're going to find out that once we find the power series, taking 10 derivatives of that is going to be very, very convenient and easy compared to the alternative. Okay, generically, what does a typical power series look like? Well, I'm going to go over two cases here. And the first one says, well, let's say that f of x is a sub n times x to the n. And of course, we're going to start at 0 here and go to infinity. And if we started to expand that out, what would we get? If I substituted a 0 in for all those n's, I would get a sub 0 times x to the 0, which is just a 1, plus the next term would be a sub 1 times x, plus a sub 2 times x squared, plus dot, dot, dot. I'm going to wrap around here a little bit. A sub n x to the n. And then here's something really, really important. Plus dot, dot, dot. We really need to have those three dots at the end here. And the reason being, if these three dots weren't here, then I wouldn't technically be going all the way to infinity. And then I would not be allowed to use the equality sign back there at the beginning. So in order to use this equality sign, we've got to make sure we have the dot, 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 and that's going to be one of those little details that helps us get over the hump when we start working on taking a practice AP exam. Now the second example is basically the same thing. It looks a little more awkward, but I want you to consider this power series, a sub n times the quantity x minus c to the nth power, okay? And it looks a little more annoying. But if we start to expand it out a little bit, we've got a sub 0 plus a sub 1 x minus c to the first power plus a sub 2 x minus c to the second power plus dot, dot, dot plus. Now we'll wrap around here a little bit. It would then be a sub n x minus c to the nth power plus, again, finish with that dot, dot, dot to show we're going all the way to infinity. And we would say this is a power series that is quote-unquote centered at the point x equals c. All right, and that doesn't mean a whole hill of beans to you right now. Hopefully we'll paint a picture in the next couple of days that gives you a little better idea, but I just want to get the terminology out of the way and kind of introduce you to a power series that isn't strictly centered at 0. If you go back and look at that first one we did, basically what we're saying is nothing was being subtracted from that x right now. So this first one was centered at c equals 0 or x equals 0. And that's what I want to do on the next slide is practice identifying where some of these are centered at. So I'm going to flash through examples here on the screen, and just to reiterate what we talked about in the last slide, we said that this generic power series here is centered at x equals c. So the first one I want to flash at you, and let's see, I'm going to be a little lackadaisical here. I'm not going to tell you whether n starts at 0 or 1 because it really doesn't matter. The key here is ask yourself, what is being added or subtracted to x before it gets raised to the nth power? And I would say because nothing, right here, nothing's being added or subtracted to that x before it gets raised to the nth power, that one's strictly centered at 0. All right, so that one wasn't that interesting. Let's spice it up a little bit. Let's take the quantity x plus 1, raise it to the nth power. Here's a good example. We would say that this one is actually centered at negative 1. All right, just the opposite of what you see. If you see x plus 1, then we say the polynomial or that power series is centered at negative 1. And now even if I threw a little extra jazz in there, what if I made it an alternating power series and did something like this? It would still be centered at negative 1. All right, our third example, a little more interesting. What if I gave you 1 over n times the quantity x minus 6 raised to the nth power? This one, we would say, is centered at positive 6 because of what's happening right here. Once you see that minus 6 there, we say it's centered at positive 6. Now, as we carry through the next couple of weeks, perhaps our most important question, the reoccurring theme that we're going to encounter over and over and over again is this quote here: for what values of x does the given power series actually converge? Okay, kind of like before Christmas there, we kept talking about, does that simple series converge or diverge? Whoops, I think I spelled that wrong. All right, that looks a little better. But now we're going to talk about, with the power series, we're going to say for what values of x does the power series actually converge. Now, recall, we said e to the x was equal to this power series right here, x to the nth power over n factorial. Now, I used an equal sign in there, and I just kind of told you to go with it. I told you that this is something we'll go over in the next couple of days. Now, the question becomes, now when I see that equal sign, I'm thinking perfect match, okay? That's what I'm thinking. I'm thinking that e to the x is a perfect match to that power series, which if we started that power series at n equals 0 and went all the way to infinity, we could start to expand that rascal out. We could substitute a 0 in there and get 1 for the first term plus x squared over 2 factorial plus x cubed over 3 factorial, and continuously take that out further and further. And like I said, we just have a very basic polynomial. So the question becomes, you know, can I substitute? Can I take something like maybe x equals 2, substitute it into both sides, you know, and can I say that e squared is perfectly equal to this power series over here, 2 to the n over n factorial? Are those truly, truly perfect matches? Okay, that becomes the question. Or, you know, does it work for every single value of x, or does it work for only some values of x? And that's the question we're going to continuously pose over and over and over again. Like, you know, okay, we said it's equal, but is that true for every value of x or just some? So we're going to focus on 3 specific outcomes. Number one, you're going to have some power series that converge, or aka, now when I say converge, I want you to continuously think of this idea, perfect match. Will the power series converge for every value of x? AKA, that's like saying we have a domain of negative infinity all the way to positive infinity. Okay. The second possible outcome is we say, well, not quite every value of x, but for most values of x. And we'll say all x's within a certain interval. Okay. All x's within a certain interval. So not quite negative infinity to infinity, but, you know, a healthy interval, and we'll say anything within that interval is legal. And then, of course, the third possible outcome is, maybe I shouldn't say of course yet, but you'll get a power series that works only at its center. It converges only at its center and nowhere else. So basically what we're saying is this is basically the worst case scenario. So at a bare minimum, every power series is guaranteed to converge at least its center, and then hopefully it'll converge for more values beyond that. All right, finally we're ready. I want to introduce you to a very special kind of power series, and the one that we're going to put all of our attention into today, and that's called a geometric power series. It makes sense that we'd start with a geometric. That was kind of been one of our friendliest ones throughout the last couple of weeks between Thanksgiving and Christmas. And I just want you to recall what we already know about a geometric series before we introduce the word power into it. And we basically said if we start at n equals 0, a and then r raised to the nth power, we said that that sum is guaranteed to be a divided by 1 minus r as long as the absolute value of r was less than 1, which is equivalent to saying negative 1 is less than r less than 1. And what we have right here is called a compound inequality, and I'm going to get in the habit of rewriting the interval of convergence within as a compound inequality. All right, now we're going to start off, we're going to keep these really simple at first, and we're going to say, you know, what if a was just a 1, okay? And then the series would look like this, and then the sum would just strictly be 1 over 1 minus r. And again, we'd still have the same interval of convergence from negative 1 to positive 1. And now we're ready to take a leap into a power series, okay? And I want you to think of a very famous function that you've seen quite a bit in your math career. I want you to think of the function 1 over 1 minus x. And this is kind of a squirrely function. It's not a polynomial, okay? First, let's agree on that. It's not a polynomial. And the graph is kind of a hyperbola-like creature with a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 0. But I want you to compare that to this rascal up here, and we're going to kind of work backwards. We're going to start here and go backwards, and I could rewrite 1 over 1 minus x as the summation of x raised to the nth power. Okay, do you notice how my x value, the x right here, corresponded to the r right here, and then I just worked backwards and rewrote it as a series? So what we've created right here is this is our very first power series, kind of a special moment, I guess, because this series is in terms of both x and n. And basically now the question becomes, for what values of x does this series converge to this function? And in other words, when are they perfect matches? For instance, am I free to substitute any value of x into both of them, or does it only work sometimes? Well, just like we had restrictions on r, we also have restrictions on this x, because x and r are kind of one and the same thing here. And we would say that this power series here converges as long as the absolute value of x is less than 1. In other words, as long as x is somewhere between -1 and 1, we have a perfect match. Okay? One last thing I wanted to write out here in your notebook, that what we have right here, I'm going to give it a special name. It's called my interval of convergence. Okay? Any x value within there creates convergence and a perfect match. Okay, so here's our first real example that we're going to dive into today, and this is going to be what we see in class tomorrow. But it's asking us to find a power series for the given function here, and they want it to be centered at 0. And I don't want you to stress out too much about centering at 0. That part usually takes care of itself. It's just something that you're going to see within the directions. And now remember, our goal is to kind of make it look like a geometric series and then work backwards into a summation form. And in other words, I'm reminding myself, I want to try to create or rewrite these in the form of 1 over 1 minus u, okay, or 1 minus r, or whatever letter you want to use down there. So just recall that 1 over 1 minus r is really equivalent to r raised to the nth power. So when we look at the function they gave us, we could say that the 2x corresponds to the r, and we've got 2x raised to the nth power, noting that the series starts at 0 and extends all the way to infinity, thus creating our equality. Sometimes it's going to be handy to break this up, depending on what they ask us to do with the power series later on in the chapter, and rewrite it as 2 to the n times x to the n. I think you'll agree that those two statements are equivalent. And then the last thing then this is kind of implied every time you find a power series, is you want to always get in the habit of writing down your interval of convergence, okay? And I'm going to abbreviate IOC. What is my interval of convergence for this particular beautiful, beautiful power series we created? Perhaps this one's a little easier to look at. Now remember, we said that r corresponded to 2x. So I'm going to say that my interval of convergence is the absolute value of 2x has to be smaller than 1. In other words, -1's got to be less than 2x, which has to be less than 1. And if I divide everything by 2, we'll isolate the x in the middle, and we'll get a real nice interval of convergence. And this is not really an ideal situation. You'll notice that interval is not very big. My in a perfect world, my interval of convergence would be from -infinity all the way to +infinity. So this one's fairly restricted, but we know it works as long as I stay within that slight interval. Now, example number 2 looks almost identical to the first one we did, and I want you to assume that there's the same set of directions involved here. The only thing we tweaked was the plus sign in the denominator now. Now, the key here is that plus sign is actually more significant than you might think, because our formula that we started with says that it's got to be 1 over 1 minus r in order to rewrite it as a power series. And if we don't have the minus sign in there, it's not the same thing. We can't say, it's close enough. So what we're going to do here is we're going to get a little fancy here, and I'm going to rewrite f of x. And I'm going to say that 1 plus 2x is really the same thing as 1 minus -2x. Okay, so basically what I'm saying here is that now my r value corresponds to -2x, and I could rewrite the power series here as negative 2x raised to the nth power. And I'm going to encourage you to kind of go one step further and kind of pull that apart a little bit. I'm going to say negative 1 to the nth times 2 to the nth times x to the nth. And these two power series here are perfectly equivalent. And I guess knowing what's going to come down the road a couple weeks from now, I'm going to prefer to maybe rewrite it as the second way, even though it looks kind of uglier. Oh, I almost forgot to talk about the interval of convergence. It's actually going to be the same thing as the last one, because the first thing you do is you say that the absolute value has to be less than 1. So it actually ends up, by the time we work the whole thing out, it'd be the same as the last one. So I'm going to kind of skip that part and move on to example 3. Our third example is a little more challenging, and assume that we have the same set of directions. They're asking me to find a power series for this particular function centered at 0. And the first thing I'm going to say is that I'm going to rewrite this function using the commutative property, where I just kind of spin it around and say 2 plus x, okay? And I want you to have this vision in your mind that we're going to try to make it look like, I want 1 minus u on the bottom. And technically, I don't really need the 1 on top. It could be any constant on top, as long as it's a constant. But on the bottom, I really need 1 minus u, where that u represents my common ratio or my radius there. So in order to create, like I said, we want this that 2 right there. We want that 2 to become a 1. So what I'm going to do is I'm going to divide every term by 2, which makes my numerator a 2. That's a 1, and then we get 1/2 x right there. Now the last thing I need is I need a minus sign there in the middle. So all I'm going to do is use a similar trick that we used on the last problem. I'm going to say 1 minus negative 1/2 of x. And again, continue to use your equal sign as you build these. That is now equal to the series. Okay, I'm going to use 2 as my a value, and then here is my r value raised to the nth power. Okay, and this one we could continue to pull it apart and so forth, and we could get things to clean up a whisker. I'm going to skip that part on this particular example so I can go ahead and talk about the interval of convergence. This series, oh, you know what? I want you to think of the interval of convergence is kind of similar to using the word domain. I think some of the math books would cringe if I took the liberties of saying so, but really essentially you can think of it that way. It's basically a list of what x is allowed to be in order to create a perfect match with the given function. And we're going to say that our common ratio has to be smaller than 1, which basically means negative 1's less than 1/2 x, which is less than 1. We took the absolute value, made it a little cleaner. And let's see, I'm going to multiply everybody by 2. So negative 2 is less than x, which is less than positive 2. And we've got ourselves a decent sized interval, a little bigger than the last problem anyway. Certainly not the ideal negative infinity to positive infinity, but it'll do. This is my favorite example that we've done so far because I think it really exemplifies the advantage of these power series. If you had to imagine, maybe integrating this function, you'd get a very messy arctan rule, and then integrating it a second time would just really be impossible for us. Or flip it around and then ask yourself, what if I had to take 3, 4, 5 derivatives of that function? Again, it would be very annoying and tedious. So creating a power series is going to be a huge advantage to us. The first thing is I'm going to go ahead and I'm going to divide every term by 2. So I got a 1/2 on top, and then I got my 1 plus my 1/2 x squared. The next thing I'm going to do is I'm going to try to create that minus sign on the bottom. So I'm going to wrap around here a little bit, and I've got my 1/2 divided by 1 minus negative 1/2 x squared. And now I'm actually ready to go. We've got it in an ideal situation. We could rewrite it as, let's see, we got an a value of 1/2. We've got an r value of negative 1/2 x squared to the nth power. And we're going to make sure we get all the little details written in there. Now in this one, I actually want to spend some time trying to clean it up just because it's going to take some practice to get comfortable doing this. The first thing I'm going to do is, let's see, we got the 1/2 in there. Because anytime you see the negative sign in there, you could rewrite negative 1 to the nth power. We also have a 1/2 to the nth power, and then we have an x squared to the nth power, which becomes x to the 2n. So we did a lot of tearing apart. Remember, just every piece in there is being raised to the nth power, and we're just pulling those pieces apart to create this long list of stuff. Now, as far as cleaning that up any further than what we've got, here's what I'm going to do. I'm going to say, in my numerator, I've got -1 to the n, x to the 2n. Now, on the denominator, what I'm going to do is I'm going to attempt to combine this fraction here with this fraction over here. And basically what I'm going to do, because I have like bases, I'm going to add those exponents, and I'm going to say that's really 1/2 to the n plus 1 power, because I got an exponent of 1 and an exponent of n. And then what I'm going to do is I'm actually going to ship that to the denominator and say strictly 2 to the n plus 1 power. So having a 1/2 in the numerator is the same thing as having a 2 in the denominator, and that's how I'm going to express my final answer. Now, as far as putting the finishing touch on this problem and talking about his radius of convergence, or I'm sorry, not the radius, but the interval of convergence. Radius is coming later. Whoops, hold on. Whoa, where'd that go? For the interval of convergence today, we're going to say that the absolute value of -1/2 x squared has got to be less than 1, which means -1's less than 1/2 x squared, which is less than 1. We're going to multiply everybody by 2. Okay. We got ourselves in a little bit of a jam here because we're going to end up taking the square root of a -2, which is a little awkward. Well, because we got this little ugly here, we basically ask ourselves, when is x squared falling within that interval? Well, x squared will fall within that interval anytime x squared itself is less than 2, because by the time you're squaring it, the negatives are pretty irrelevant, and I'm just going to finish off by saying that's my interval of convergence. Well, we can kind of celebrate here. This is our last example of the day, and I want to stress, if you're feeling rather overwhelmed right now, that's okay. That's very normal for our first experience with Power Series, and we're going to really focus on tomorrow in class, just kind of working through these together and trying to build each other up. But I wanted to finish with one that wasn't centered at 0. And here, it's such an innocent-looking function here, but it's such a crazy problem when you try to center it at something. Well, I shouldn't say it's that crazy. I think once you see it the first time, you'll be like, that's pretty easy. I can do that. But I want to get creative here, and I want you to think of 1 over x and rewrite it as 1 over 1 plus the quantity x minus 1. All right. Now, there's 2 advantages to doing that. First of all, I want you to ask yourself, if I simplified the denominator right here, do you agree that the 1's would cancel out and that it truly is equivalent to the x that I started with? So I just kind of threw in some extra stuff. I added a 1 and I subtracted a 1 to create an equivalence there. And now, the advantage to what I wrote is that I've now created an r value of x minus 1. And x minus 1 is what I was shooting for, so that it would be centered at +1. The only thing left here, and this is slightly annoying, is I've got to try to create a minus sign in the middle. So I'm going to use the old trick that we've been using, where we think, okay, it's going to be 1 minus, and then we're going to negate what's inside, and I'm going to say -x plus 1. Okay, so now we've gotten it in the mold or the form that we've been shooting for all day today to make it look geometric, and we can now say that that's equivalent, and I want to make sure that we've got equal signs running all the way through these. That's equivalent to this power series right here. We've got our r value of -x plus 1 to the nth power. And now we're going to take that a step further, and I want you to factor out the -1 and say -1 to the n, so it actually becomes an alternating series. And now you've got x minus 1 to the nth power. You can clearly see that this is centered at 1 now because of the x minus 1 in parentheses. And then the only thing left for us to do today, oh my goodness, what happened there? Okay. The only thing left for us to do is to find the interval of convergence. And we're going to say that our r value, the absolute value of that r value, has to be smaller than 1, or in other words, it's got to fall within this special interval. And in order to isolate that x in the middle, which is always my goal, is to try to isolate that x, is I'm going to add a 1 to both ends and say, well, 0 is less than x, which is less than 2. So basically, let's summarize what we've decided here. We have decided that for any value of x that falls within the interval of 0 to 2, that this power series right here is a perfect match to this function right here. These two are perfect matches as long as I stay within the interval 0 to 2. Once you leave that interval, you are moving at entering at your own risk. But we have a guarantee that within the interval 0 to 2, we have convergence and a perfect match. So, ladies and gentlemen, I hope we've taken good notes. I hope we've had a high degree of focus, and we're going to work real hard tomorrow and get back in the groove. And we'll see you then.